Oh, there we go. We're online. Good. So we've looked at permutations, and permutations, we're taking a group of objects, we're selecting some. Order matters, okay? Like which one is in the first position, which one is in the second position, which one is in the third position. Today we're going to do combinations. And combinations, order just doesn't matter, okay? So this is an inappropriately named device. This is called a combination lock, but actually it should be called a permutation lock because it really, really matters what order you put the numbers in. So this should be a permutation lock, not a combination lock. Like if the combination is 8, 32, 16, you can't put in 32, 8, 16 and open it. This is a permutation lock, not a combination lock. Okay. There we go. I think once this gets out on YouTube, we'll probably revolutionize the lock industry. I think you're going to see them changing the name of those kind of locks. Okay. Anyways, as you can see, we have the biblical battle between dinosaurs and mammals here. We have 9 dinosaurs here, and we have 5 mammals. Okay. Now, the good thing about animals is everything is equal. If you pick a bunch of animals, they don't know who's president or secretary or who was chosen first or anything. So when you're talking about dinosaurs in particular, you know you're talking about combinations, not permutations. So here's my question. How many ways can I choose? Can I choose 3 dinosaurs from a group of 9, because I have 9. Okay, so back in the good old days when order mattered, we used this expression. How many permutations are there if I select 3 objects from 9? And if you'll recall, there were a couple of ways of expressing this. This very specifically says 9 factorial over 6 factorial, which is the same thing as 9 times 8 times 7. Okay, so here we go. I'm just going to randomly pick 3 dinosaurs here. There we go. And so I've chosen 3 dinosaurs. And you know what? Order doesn't matter. They're going to wander around like dinosaurs. There is no first, second, and third. We have to just figure out how many combinations there are rather than permutations. And so it becomes this simple matter of just dividing out the number of permutations that there are of 3 objects. Okay, so we're going to take this 9 times 8 times 7, and we're going to be dividing it by 3 times 2 times 1, which is the same thing as taking 9 factorial over 6 factorial and dividing it by 3 factorial. Okay, so you notice the pattern here, 6 and 3 is 9. We express this in a slightly different way, and you'll see this on your calculator. Instead of a 9p3, this is 9c3. So how many, you have 9 things, choose 3 of them, and you don't care about order at all. All right, this winds up being 504, I think. No, it doesn't. It winds up being 504 divided by 6, which is 84. All right, so imagine that. There are 84 different combinations of 3 dinosaurs when I choose them from a group of 9. Okay, so there we go. There's the idea of a combination. Order doesn't matter. It's just a bit of an extension of permutations where we divide out all the permutations of the selected objects. You'll notice that this is the expression that will do it for you. Notice that 6 and 3 both add up to 9, and your calculator has this 9 choose 3 notation on it. All right, let's make it more complicated. Back in the days of the dinosaurs, before they were wiped out by smoking cigarettes, there were some mammals around, just little tiny mammals running around. And so we have a representative sample here. We have 9 dinosaurs, and we have 5 mammals. Okay, let's say there's going to be a giant flood, and I'm trying to decide, you know, I want some combination of dinosaurs, and I want some combination of mammals to go with me on my boat that I might build. Okay, so out of 9 dinosaurs and 5 mammals, how many combinations of 4 dinosaurs and, I don't know, how many mammals am I going to pick? I'm going to pick out 3 mammals. Are there? So as you can imagine, if you're trying to save the animal kingdom from a giant flood, there's an awful lot of possibilities here. Now, this is where we use that multiplicity principle. So we're combining combinations, multiplicity. What do you know? Multiplicity, it ends in city. Okay, this is where we have a multiplicity principle because we're going to be choosing 4 dinosaurs from 9, and we're going to be choosing 3 mammals from 5. So it's a 2-stage process. And so first of all, we're going to choose our 4 dinosaurs from 9. And that can be combined with that second stage where I choose 3 mammals from a group of 5. And so I'm using just combinations because order doesn't matter. Once I get them on my arc, they're going to run all around and act crazy. Okay, so, isn't that a coincidence? Wouldn't you know it? My calculator doesn't have NPR and NCR on it. I can't do this on my calculator. Okay, however, I'm going to turn to the internet for the answer. 9 choose 4. Does anybody in the internet have the answer? Yeah.
126.
126. So there are 126 different combinations of 4 dinosaurs chosen from 9. And now I'm going to choose 3 mammals from a group of 5. And so internet, what's the answer to that?
10.
10? That's not exciting. I guess so, because this is 5 times 4 divided by 2 times 1, so that's 10. And so there we go. I only have to go through about 1,260 different possible combinations to put on my arc of mammals and dinosaurs to decide which species will populate the Earth after a devastating apocalypse. So don't let anybody tell you that combinations aren't important.